2, 1. Okay, so introduction to odd, even, continuous, and discontinuous functions. So I'll talk about this a little bit because I think when you're starting your advanced functions, kind of as an introduction, I hope your teachers will introduce you to these topics, and I'll try to give you a few examples to see it visually, how it looks like, and then also kind of algebraically in terms of a function. So we'll start off with just odd and even functions. So what are these? So as you can see here, I kind of put down the definition of them with respect to the values of your input, your independent variable, your x. So if you have an x, and for an odd function, you take the negative of that input, it turns out that if you substitute it in, you will get your original function back, and you'll have it negative as well. So what does that actually mean? So here's a very simple one. So we all are very familiar with, let's say, y is equal to x, all right, which basically looks like a line, right? It's a slope of 1, goes through the origin. Now notice that if I kind of rewrite this and say, okay, so let's call this as a function. So instead of y, I'm going to use f of x, okay, is equal to x. If I now substitute, okay, so inside of here, so if I substitute negative x in here, what I'm going to get is, well, if I substitute negative x for this, this is just going to be negative x. And notice that now, indeed, your f and then substituted negative x for it, which is exactly what you see here in the definition, it will give us the original function back, which is just negative of f of x. All right, because f of x is just simply x, okay, and that's what we had right here. Okay, so that negative pops out right in front. So you have these types of functions being odd. Now, it turns out that actually, if you remember power functions, maybe I'll put up a link up above there, okay, kind of from grade 11, and these ones, I'll kind of simplify them in a sense. Let's say that they looked kind of like this. Okay, and it was x and it was raised to some power n. Now n could have been 1, 2, 3, and so on. And now, if you take, okay, x and this n, where this n is going to be actually odd, so if it's equal to 1, well, then it's going to be back to this function that I did. If it's 3, so x cubed, okay, so that's a power function with a cube, and then it's 5 and 7 and so on. So if it is odd, it actually guarantees for us that we're going to get an odd function. So I don't know, but I would sense that maybe it had something to do with these power functions, and we started calling them odd functions because it was odd, okay, for all the odd kind of numbers that we had, so 1, 3, 5, and so on, that it had this property. And here, so I'm going to just show you one. Let's say if it was x cubed, all right? Say if our f of x, okay, was x cubed. Now, if I substitute negative x for it, so it's almost like, the opposite. Let's say if it was 1 and then I substitute negative 1. Well, then what I will get is, so if I substitute in here, then I'm going to get this. But what does this equal? Well, the 3 works on the negative, right, that you see there. So that's going to be just a negative, because negative 1 cubed is still negative 1. And then I'm going to get my x cubed back, which is just negative of my original function. All right, so we have f at negative x is equal to negative of f at x, okay, our original x. And that's what makes it odd. And you can do that with numerous functions. They don't have to be like this. There can be, many others that you can do. I mean, for instance, you can think about, okay, in terms of these odd functions that we have. You can even go back to sines and cosines, and then think, oh, okay, our sines and cosines going to be positive, or are going to be odd, okay, or well, they're going to be even. Now, I want to just show you how these things look like on decimals. So for odd functions, so what we have, if I bring back decimals in here, so let's say f, okay, at x is equal to x to the n. All right, and I'm going to put, let's say n in here. And I start graphing this, all right? So this we know was just our line when we said that this was odd. And notice that what it looks like, that it kind of goes in, and on one side, it's almost like there's some kind of symmetry, like odd symmetry that happens within these. Now, if I do this and put cubed, so this is going to be x cubed, right? Again, we have that kind of odd symmetry happening. And it's true for all the power functions, right? That you're going to have this. Now, do they have to do odd functions are only power functions? No. Okay? But in order to test it, you can always kind of plug in negative x and then see if you can manipulate the function, and it will give you negative f of x back. And if it does, then it's considered an odd function. So it has that. Now, for even functions, so if I go back in here, so for these even functions, so even functions have this nice property that both, if you substitute negative x in here, it will actually give you the original function back if it was just f at x. So there's kind of like symmetry almost, I would say, almost like that there's, on the y-axis where it just kind of reflects back. And there are many functions like this. Now, notice this is not going to be the case with, let's say, y is equal to x, because if I substitute negative, it's not going to give me the x back the way that I wanted. But, a very common one, and one that we, talked about in advanced functions a little bit, which was the absolute value. Put up a link up above there. So that one had a very nice property that if you took it, so f of x is equal to, so absolute value of x. So we know that it, kind of looks like this, right? Because it just takes the absolute value. And notice that the symmetry. So let's say, if this was my x, this is my y. Okay, so at this point, it kind of is reflected back. And let's say if this was if this was x right here. So that was x. Okay, and if you reflect it back on negative x, okay, it's still going to give you the same value back. Why? Well, because if I substitute negative x in here, so if I take f and negative x, substitute it back in here, well, what does the absolute value do? The absolute value just takes the x on its own, and therefore it is equal to f of x. All right? So that's what you have here. And this actually you still had in your power functions. So if I go back in here to this power function right there, and I start looking at these, now notice for the odd values of n, so 1, 3, 5, it was an odd function. So you'd probably guess that if you had even, right, 2, 4, 6, and so on, all of a sudden it's going to turn out to be an even function. So again, most likely that's something to do, okay, with this power function. So all your even values that you have, okay, within here, so let's say, let me remove this, okay, from here. So if I remove this out, and let's say I put f of x is equal to, let's say x to the 4. Now, if I substitute f at negative x into this, then what I'm going to get is that. But now again, so we know that that negative, right, because their exponent is 4, okay, because it's even, so all of a sudden, all we're going to have is x to the 4, which is equal to f at x. So it is an even function. So that's what we have. Okay, so there's a lot of symmetry that we have within here. All right. Now, if I graph this, so if I go back to decimals in here, okay, and let's say now I would put, let's say 2, we know that this was kind of symmetrical, right, in some way. And the beauty of this even thing, so it doesn't matter what point you pick, okay? So if it's, let's say, 4, okay, and then negative 4, because of the symmetry, the beautiful symmetry that we have, okay, it is actually even. So that's pretty cool, right? Now, it doesn't have to be just power functions. It can be even a combination, okay, of, some other function. So for instance, I'll give you another one. Say g of x is equal to, and I'm going to kind of make this up, x, say to the 4. Let's make it a little funky. Okay, I'm going to close this one down in here so we don't see it. X to the 4, and minus 3x squared. Okay, so this one is a neat one. Okay, So notice it's not exactly a power function, it's a combination, right? So it's a polynomial function that we have. Now, is this symmetric, right? It looks kind of symmetrical, right? Is it even that we have? So what would we have to do to test if this was even? Well, our test, so let's see if I remember this. So if I take this, let me remove this junk. So if I take this, and let's say, so our new one, well, I called it g of x. So let me do that. Right, the g of x is equal to, I think it was x to the 4 minus 3x squared. Okay? So that's g of x, right? Or you can just say f of x. Now, if I substitute a negative in here, well, what's going to happen? It's going to look like this. 3. Again, I'm going to substitute the negative. But hey, wait a minute. Because these are even, that negative is going to disappear. And I'm going to get back just my g of x. So indeed, for all the x values that I have, this is actually an even function. And you always kind of test it throughout, okay? So don't forget, I mean, sometimes, within your functions, you may want to test. Notice I've always been substituting x because it has to be true for all x. It can't be just true for one and then not the other, right? So it has to be true, so odd functions and even functions, this principle has to be true for all of the x's that we have, for them to be odd and even, all right? So that's one. Now, another interesting function, I said sines and cosines, so I'll end it with that. Now, if we plotted, sine of x, okay? Let me just do that. So what does this look like? Would you think that it's an odd function? Let's see if you remember your trigonometry or not. Or is it an even function, right, in some way? Well, it is an odd function, okay? So I'm going to let you test that yourself. If you substitute negative x in there, okay, and notice I'm going to do that right below. Now I'm going to cheat because I can actually use decimals to show you this. So if I put negative x in here, okay, so if I have this, now substitute it back in, now notice that all of a sudden that it flips, which means that it should be, because it's odd, that means it should be the negative of our original function. And if I do the negative, it gives me exactly that back. So it satisfies the principle, right? At negative x, it gives you negative f of x back. So this is odd. So sine is actually an odd function. Now, how about cos? So if I remove this, then you probably are guessing, okay? So if I do this, and now I do this, notice they're on top of each other. So this one is even. So cos is actually even. And you can do that for many other functions. You just have to test this out. So that gives you a little bit of a sense and an introduction to odd and even functions. Now, what about this topic of continuous and discontinuous, which initially, you should get kind of introduced to it, and then slowly you should start understanding what's the difference between these two. So I'm going to try to do it kind of in an informal way, all right, so that it gives you some sense. Now, what I will tell you is that continuous functions do not have any break in them. There is no gap at all that happens at any point from one point to another. It's a smooth and it kind of goes in continuously from one to another. So here, notice there's no gaps in between here. Okay, so this was some kind of probably a parabola. I mean, I didn't graph exactly what it is. I just want to show it to you visually so you can get some intuition. Now, the one on the right, this one, so notice it's continuous here. So it's continuous all the way here. There's no gaps. Now, it looks like, because there's an open circle there, so it's not defined at that x is equal to 0. And all of a sudden, it jumps. And there's a gap. And then again, it just goes in and it's continuous. So at x is equal to 0, this, okay, graph right here that we have, okay, this would be discontinuous. There is actually a break, okay, that we can gap up. And I always like to think, can we stick a little line segment in between, so that it creates a break and then we're not touching anything on the actual function itself. It's still a function, right? Because if you do the vertical test, at least for these values, right? We don't know what happens, okay, on the edges here. But at least for these, okay, it's still a function. passes your vertical test. Okay, there's only one value. Notice even at x is equal to 0, because it's not defined here, but it is defined here. So it still only has 1. But it's discontinuous. And here, it looks like there's a line, right? That just keeps going. However, what they've done is they said, oh, here, and it doesn't have to be always at x is equal to 0. It could happen somewhere else. But here they say, oh, look at that. It gaps down. So there's a break in our actual function. So again, I can kind of draw a little line segment in between because it has a gap in between. All right? So this one would be discontinuous, but only at that x is equal to 0. Now, can it happen at multiple points? Yes, it could happen. I could have drawn this line and, made an open circle here, and instead, maybe plotted one right there, okay? And that would have been discontinuous at whatever value that is. So it's continuous everywhere except at these two particular points. And it can happen on many points. Now, this one, okay, which kind of looks like, it's like a haircut type of style that's happening there. So, is this continuous or discontinuous? Well, it just keeps going in here. Now, there is, a little cusp in there, but there's really no break, and it just continues on. It's still a function. It only has one value for each x, at least for the ones we see. So this one would actually be continuous, right? Because there is no official break. So that's how you can kind of intuitively think. Are there these breaks or are there no breaks, okay, within whatever domain we're working with, okay, or the interval that we are working with. So that's a little bit of a heads up for you in terms of thinking about continuous and discontinuous, because you might hear those words as you go along your advanced functions course. All right. If you have any questions, you can leave them down in the comment. Hopefully you can hit a thumbs up and see and continue the 1 million journey. Let's keep it going, right? So share it, spread it. Hopefully these videos help a lot of other students. Okay. Cheers, everybody. Bye.